Welcome to this video lecture on the general linear model. In Chapter 6 and Chapter 7 of this textbook, we have been performing somewhat similar tasks. In each case, we have been predicting the value of a continuous response. In Chapter 6, which deals with regression, we have used one or more continuous predictors to predict the value of the response. And in Chapter 7, where we've studied ANOVA, we have used one or more categorical predictors to predict the value of a response. We can combine both of these approaches using the general linear model, which includes regression models, ANOVA models, and a combination of those, where both categorical and continuous predictors can be used in the same model to predict the value of a response. The general linear model is sometimes referred to as ANCOVA, meaning analysis of covariance, where a covariate is a continuous predictor which is observed rather than controlled. There is an even more general approach called the generalized linear model, which does not make the assumption that the response is normally distributed. And so the generalized linear model includes, for example, binary logistic regression models. But we will give our attention to the general linear model. We will assume that the response is normally distributed, but we will use a number of predictors, some perhaps categorical and some continuous, in order to predict that response. Here is an example where we will use a general linear model to predict the VO2 max of athletes. The VO2 max is a measurement of oxygen usage, and so it's a measure of the endurance of an athlete. This data set on which this analysis is based came from a number of hurlers who play hurling in County Dublin. This model uses two predictors, the age of the player and the position of the player, to predict the VO2 max. Notice that age is a continuous predictor. Age is a number, while position is a categorical predictor. Position is a category. 4 categories: goalkeeper, defender, midfielder, and forward. The ANOVA table that is produced by the general linear model provides a p-value for age and a p-value for position. And you notice that both of those p-values are below 5%, telling us that age is a useful predictor of VO2 max, and so is position. The output also provides us with a regression equation with a common slope for age, but with a different intercept for each position. So this is similar to performing a regression analysis and including some categorical predictors. Let's now talk about repeated measures. Repeated measures experiment is an experiment where a number of subjects, who could be, for example, patients or athletes, are observed at different time points. For example, before and after an intervention, where, let's say, a dietary regimen or an exercise regimen is prescribed, and then the condition of the subjects after pursuing this regimen are observed to see if the regimen has made a difference. We can use a general linear model to analyze the data from a study like this. And so the p-value for time will indicate whether there's an impact due to the intervention. If things change over time, where of course time includes an observation before and after the particular intervention was made. The subjects in this experiment will be random factors, something we will talk about later on in this set of slides. And in the design, we can include subject characteristics as covariates, things like their blood pressure or their body mass index. And it may be that the impact of the intervention is somewhat dependent on these characteristics. We can also include some categorical factors such as their gender or their playing position. And if we find that there's an interaction, a significant interaction between time and other factors, then that indicates that the impact of the intervention does depend on the subject characteristics, that perhaps this intervention works better for men rather than women, or works better for people who play in a certain position, or people with high blood pressure, or something else. So the main purpose of the repeated measures is to explore the impact of the intervention, but it also takes account of whether that intervention may be related or dependent in some way upon the characteristics of the subjects to whom the intervention is applied. Now to talk about this issue of what we mean by fixed and random factors. Let's say we do an experiment where we study the effect on writing speed of the two factors, person and hand. In the case of hand, there are only two levels of that factor, left and right, and both levels are included in the experiment. So every possible level of that factor is included. When that is the case, that is called a fixed factor. Left and right are all the levels of interest. Left and right are both included in the experiment. And when we perform the experiment, we can pick the winner. Which hand writes faster, the left hand or the right hand? Random factors, by contrast, consist of, if you like, a random selection of all the factors that are available. The factor person has many billions of possible levels, since there are many billions of people in the world. But in the experiment, we can only include a certain number of people. And so we include a number of people, not just because those people are interesting in themselves, but because they are in the experiment in order to represent all the other people, because we want to see what kind of differences arise from person to person. So person is a random factor. And we are not so much interested in picking the winner among the persons, because the persons in the experiment are not even the persons who are most interesting to us, because we're interested in all the people who will use our intervention later on, who are not present in the experiment. So we're not interested so much in the p-value and in picking the winner. We are interested in the p-value because it tells us that person does have an effect. But not just in order to pick the winner out of the people present in the experiment, but in order to see how much variance is due to the factor person. And so we can produce the variance components, which shows us this. And in this case, we see here that the variance due to person is presented, and that's shown as a percentage of the total. 78% of the variation in writing speed has to do with the person doing the writing. You'll notice that it's also presented as standard deviations and percentages, but notice that the percentages for standard deviations do not add up to 100%. You will recall from discussions we've had earlier in this textbook that variance is additive, while standard deviation is not. So the variance component becomes interesting for our random factor. It tells us how important that factor is in giving rise to variation in the response. We now just have a word about nested designs. Most of the experiments we have performed so far have been crossed designs. That is, where we have had two factors in an experiment, every combination of those two factors have been included. For example, when we did an experiment on driver and vehicle to explore the effect of those two factors on fuel economy. In that experiment, every driver drove every vehicle. Every combination occurred. Or if the drivers were represented by rows in a table and the vehicles by columns, every row crossed every column at a certain cell, and in every cell there were some observations. Now, in some designs, it is not possible for the design to be crossed. Instead, there are times when the factors are nested or in a hierarchical design. For example, suppose we are interested in measuring the length of leaves on a tree. So the response is the length of leaf. And the two factors of interest are tree and branch. We want to see if leaf length differs from tree to tree and if leaf length differs from branch to branch. Now the branches are within the trees. A branch which is on tree number 1 will never be on tree number 2. So we cannot cross the factors. Instead, the branches are nested within the trees. Or if you prefer, there's a hierarchic structure where the tree is the top level of the hierarchy and the next level after that is branch. And of course, interaction cannot happen. There is no interaction in a nested design because a branch will never be on any other tree except the one that it's on. When we do an analysis of variance for a nested design, of course there's no interaction term, and also the nesting of factors is respected. You will notice that brackets are used there. Branch brackets tree denotes that the factor branch is nested inside the factor tree. Now, if you look at the p-value for branch, you will notice that it's less than 5%, which indicates that the leaf lengths are different from branch to branch. Branch has an effect on the length of leaves. When we go to study the effect of tree, in this particular ANOVA table, the p-value is not less than 5%. So we do not have evidence that there is an effect due to tree over and above the effect due to branch. Now, when we are calculating the F statistic for tree, we divide the mean square for tree not by the mean square for error, but by the mean square for branch. Because when we are comparing the trees, the question we are asking is this: is there an effect due to trees which cannot be explained by the effect due to branches? So at any stage in the hierarchy, when we are asking the question whether that factor affects the response, we treat the next level down in the hierarchy as the error variance. So again, just looking at the F value for tree, 0.45, it's obtained by dividing the mean square for tree by the mean square for branch, not the mean square for error. Because when we look at leaves on different trees, of course, they must be on different branches. They cannot be otherwise. But we're not asking the question, are there differences due to branches? We're asking, are there differences due to trees over and above the differences that exist due to branches? You can read more about this in the textbook in chapter 7.